User datagram protocol is a connectionless protocol for data transfer. We see here in the OSI model UDP is in the transport layer. UDP is a lightweight protocol. It provides connectionless transport layer service and there is no handshake or connection process. UDP does not have any ordering or reliability services and there is no teardown. UDP is a lightweight protocol that's great for time-sensitive applications such as DNS, voice over IP, routing information protocol, or trivial file transfer protocol. Here we see the UDP header. It's always 8 bytes long and it includes the source port, destination port, length, and checksum. Now that checksum is used for error detection, not correction. The UDP checksum is optional with IP version 4. However, it is mandatory with IP version 6 primarily because IP version 6 does not have a checksum. Now let's take a look at the UDP header. I am at the Wireshark and if you would like to follow along, you can just simply go to this export and download this file and bring it into the Wireshark. Now I have opened it up in the Wireshark and what I will do up here is go to the display filter and I will type UDP. So there are my DNS packet and what we will do is just take a look at the user datagram protocol. I will double click and it will pop out this frame, and again this lightweight protocol only has 4 fields: the source port, the destination port, the length, and the checksum, and that's pretty much for the UDP. So while I'm here, let's take a look at some other things in Wireshark. Let's go to the statistics. If we go to the statistics, you can see there are a lot of choices, and for more advanced training we will get into those, but for something really simple, let's just take a look at the capture file properties. Now when you open this tells us a summary about this file. Now you can see the capture and what it knows about the hardware, the operating system. Again, what it knows it will put in there. Here you can see when this packet was captured, 2011, and some more information about the statistic. And now down below here is the next generation. We are able to put comment in the file. Now this would be handy if we were to share this information with coworkers. So for example, I might want to say take a look at frame 29. And I will just say save comment and then we'll close it. Now if you take a look up here, there is a asterisk that is right by the title. That is because it knows that there is a comment and you will want to save that so someone can reference it when they open it up. Well, we'll go back into the statistic again and I will drop this down, and another handy tool is protocol hierarchy. Now this is helpful if you are taking a look at the protocols that are traveling on your network and you might want to see if there's anything that should not be on your network. So this is simple capture, nothing really standing out, but again it's a nice handy tool. I will close that too here. Now there is another thing in this statistic and that interesting. I will talk about some of the things with conversation and endpoint. We will take a look at the endpoint. Now remember, the endpoints are the two sides of the conversation. These are the endpoints. If we go into the conversation, here you can see details about the conversation. In this case we have minimal information. It's very short capture, but if we go into the one conversation and we have a little bit more detail here, I can right click and I can say apply as a filter and select it, and here you have choices whether you want to A to B, B to A, or both ways, and I will say close and that's put that conversation filter right up there, and it runs it for you so that you can see the whole stream. So really that's all there is about UDP. And again, I wanted to share with you some other things found in Wireshark. So UDP is a connectionless protocol for data transfer. The Internet Protocol resides at the network layer of the OSI model. For this segment, we will focus on IP version 4. The Internet Protocol is responsible for addressing and routing its connectionless, meaning its best effort. For example, if you were to send a letter general delivery, it will get there, but there is no guarantee. But we can provide quality of service to push the data along a little faster. Here's your IP version 4 header, and as you can see, we have several fields, and at the bottom option and data. Let's take a look at an IP header. I am in the Wireshark and I have expanded one of the frame, and we will take a look at that header. And on the right hand side, you could follow along. Alright, the first field is simply version, and in this case it is version 4. Not much there to show. This tells us the header length, and it is 20 bytes. And I can confirm this if I just put my cursor on top of this Internet Protocol version and then look down here. You can see it's 20 bytes. This field value here is called differentiated services that relate to what called the type of service. Now keep in mind, 0 is best effort. It's not prioritized, but in certain cases we want the data to prioritize and move along a little faster. The total length is header and any data that follows, and here we see 1500. Now the next three fields relate to the fragmentation. Those are identification, flags, and fragment offset. The specification stated that IP was responsible for addressing and fragmentation. Now that was a long time ago, but things have changed. We don't see fragmentation so much anymore. So those three fields you see, the first one is identification. So in the case of fragmented packet, you see a number of different fragments. You will need to identify them to put EM all back together. Then there is the flags, and I'll drop this down. Now you see the first one is the reserved bit, and that's not ever used, and the second one is don't fragment, and sometimes that's 0, but a lot of times it simply says don't fragment me, don't break me apart. Now if we were to fragment, in some cases you will, for example, if you are in the virtual environment and you use jumbo frames, well then you go back out to the regular network and it's a lot smaller and you have to fragment. So in this case you would see more fragment, and that bit would be set. And the last field value is that row is fragment offset, and that identifier would help you to put back the fragments in the correct order, in the correct place. The next field is the time to live value, and that's essentially how many hoops it takes around before it goes to the 0, and if it does not go to 0, then it's no longer going to exist. The time to live value is in order to prevent the packets from going around and never getting to their final destination. Now this, you see the protocol TCP. That protocol field is what follows the IP header, and down below here you see TCP, so that's what the identifies. And then you see the header checksum, and in this case you see the validation is disabled, and we do disable the validation because sometimes it's offloaded and the checksum's incorrect, so it tells you what it is, but it is not checked. And then down below here, this is where you see your source and destination IP address. Then after that you see any data that would follow. So that's the Internet Protocol version 4. Internet Protocol version 6, like Internet Protocol version 4, resides at the network layer of the OSI model. IP version 6 has a number of features, one being a larger address space. IP version 4 had a 32-bit address space. It was represented by a dotted decimal notation. IP version 6 uses 128 bits in the address space, and it's represented using hexadecimal notation. IP version 6 supports both stateful and stateless auto configuration. With IP version 6, there is no broadcast. IP version 6 uses multicast to communicate with multiple hosts. IP version 6 has a streamlined header. you will see that there are a lot of fewer field values in IP version 6. There are optional extension headers that you can use with IP version 6, including fragmenting or IP security. IP version 6 is still connectionless and a best effort protocol and requires the use of ICMP version 6 along with it. The main enhancement, as you can see in this illustration, is that IGMP and ARP are not necessary with IP version 6. Let's compare the IP version 4 header with the IP version 6 header. Now we'll take a look at the field value. First, the internet header length does not exist in an IP version 6 header. Those three fields, the identification flag and fragment offset, had to do with fragmentation. IP version 6 seeks not to fragment, so there are no fields that deal with fragmentation. You can fragment, but you will need to use an extension header. The time to live value still exists in an IP version 6 header, however it's called hop limit. And there is no header checksum in an IP version 6 header. Now I have opened this packet capture and I filtered by IP version 6. Now let's take a look at the field values. Okay, I will put this up at the top so you can take a look at it, and we'll go through each of those field values. There are not a lot of them, but let's take a look at the first is the version. It says version 6. Not much to see there. We know that that's what the version is, but the next field value is called traffic class. This has to do with quality of service. The default is 0, meaning best effort, and then we see the flow label. The value is 0, and that's because the flow label is experimental and not really to be used. Now we look at the payload length. The payload length is any header or data that follows the IP header. So let's take a look at the UDP header. You can see it's 8 bytes. And the locator ID separation protocol here you can see is 76 bytes. So 76 plus 8 equals to 84. There we see UDP that follows the IP header, and that's what follow it. And then we see the hop limit. The last two field values are the source and destination address. In general, you are going to see a lot more IP version 6 on our networks, so you will need to get familiar with IP version 6. ICMP or Internet Control Message Protocol resides at the network layer of the OSI model. ICMP is an integral part of the Internet Protocol and must be implemented by every IP module as it's part of the original RFC. The fact is the Internet Protocol would be nothing without ICMP. It's a very important protocol. With ICMP, there is no data exchange, it's simply error reporting, and it's also used by the utility ping for echo request, echo reply messages. As we see here in this graphic, we can split the ICMP messages in two categories, error reporting and queries. For error reporting, you could have things such as destination unreachable, source quench, or time exceeded. For the query, you would see echo request reply, timestamp, or address mask. The ICMP message are transmitted with an IP datagram. So here we see an illustration of the IP header followed by the ICMP message. Within that ICMP message, you will see some commonalities such as the type, the code, and the checksum. The content will really depend on the type and whatever possible code that you might see. IP is unreliable and does not guarantee delivery, so it's important to notify the sender when something goes wrong. ICMP is used to give feedback about network problems that are preventing packet delivery. When an ICMP error message is sent, the message is always going to have the IP header and then the first 8 bytes of the original datagram that caused the error. As we see here is an example, destination unreachable, the type, the code, checksum, and then the internet header and first 64 bytes of the original datagram. I'm at this web page, Anna, and here you can see all the different types of ICMP messages. There are quite a few, but I want you to pay attention here. As you can see, there are several that have been deprecated for one reason or another, and you should avoid using them. The one that you will use and is important to use is the type 3 destination unreachable. Within that you see the different code, such as the network is unreachable, the host is unreachable, or the protocol is unreachable. Let's take a look at the couple of different example. I am at the packet life. I am going to take two of these packet capture, ICMP fragment, and here this trace route MPLS. The first one I have opened is ICMP.fragmented, and in this case what we can see is this is an echo reply. So we see that it tests for reachability and is able to reach the host, and we are able to reply, yes, I did reach the host. So we see the IP header, and then within the ICMP header we see type, the code, and the checksum, and then data, which is essentially nothing. So nothing bad happens, it's just a test for reachability. Now in this example, this is a trace route. We know with trace route it purposely times out, so it's going to report back that I was able to get to this hop and then report how long it took. It comes up black because it thinks it's an error, but I will take that coloring off. But what might be fun is, let's go to the statistics and do a flow graph just to show you how it made its journey, and you can see all of those as it's going from one hop to another and then reporting back. Now because it's coming up as an error, we can see exactly what happens. As we know that if there's an error message, the message is always going to contain the IP header and then the first 8 bytes of the original datagram that caused the error to be generated. So in this case you see there's your time to live exceeded. So there's your IP header, and then we will blow out the ICMP header, and as you see the type, the code, and the checksum, and then in that you see the IP header and the first 8 bytes of the original datagram. So those are two examples of ICMP. ICMP is a powerful protocol, but we have to understand that it's also used in malicious ways. For example, ICMP is used in reconnaissance by Kali Linux. It could be used to do reconnaissance, to do a ping sweep, or to evade firewall rules. So the question is, what type of ICMP packet are you going to allow? The only really essential ICMP traffic is type 3. That's your destination unreachable, and then the codes that fall within that. The other are optional. The type 0, 8, and 11, those would be optional. Depend on whether you would like to allow those on your network or not. So Internet Control Message Protocol, or ICMP, is used by routers, intermediary devices, or hosts to communicate updates or error information. ICMP is essentially a code for the Internet Protocol, making sure the route is clear and communicating any error. IMP version 6, like ICMP version 4, resides at the network layer of the OSI model. ICMP version 6 is a very important protocol. It must be implemented by every IP module. Now we have said this before, but now let's take a look. We will go to the source. I am at RFC 4443, and then right here it states ICMP version 6 is an integral part of IP version 6, and the base protocol must be fully implemented by every IP version 6 node. Now just like ICMP version 4, no data is exchanged. It used to communicate updates or error message, and it also used by the ping utility echo request, echo reply. Now here we see the IP datagram where we see the IP version 6 header followed by the ICMP version 6 message. Now that ICMP message is just like IP version 4, where you see the type, the code, the checksum, and then the contents will be depend on the type and the code. But unlike ICMP version 4, ICMP version 6 has a lot bigger role. Keep in mind, IP version 6 does not have any AARP or IGMP. As a result, ICMP version 6 assumes those two roles. The messages includes error message, information message, neighbor discovery message, including the neighbor discovery protocol and group membership message that includes multicast listener discovery messages. We also of course have error messages that includes destination, unreachable, packet too big, time exceeded and parameter problems. The information message includes echo request and echo reply. IMET packet capture on the packet life, and you can follow along if you like. We will take two simple examples: IMCP version 6 echoes and IP version 6 NDP cap. Now I have opened up the echoes and just a test for reachability. And as you can see, we have our ping request, ping reply, pretty simple. And down below you can take a look, you have your IP header. And then your ICMP version 6 header and then the information within it. Well, now sometimes you might want to just follow what is happening there with ICMP. And if you just right click and we say follow. Well, we can't because there is no transport layer protocol. This is an SSL stream or an HTTP stream, but we can do this. Let's go to the statistics, and in flow graph, you can open the flow graph and there you can see the test for reachability and with the request and the replies. And then you see the neighbor discovery protocol, and there's a lot of activity going on within this. We see the multicast listener report, neighbor solicitation and the neighbor advertisement. And again I will take a look at the statistics here and I will move to the flow graph. And here you can see the flow as the traffic is going back and forth communicating to other devices on the network. And if we did take a look at the neighbor advertisement, we will blow this out. ICMP version 6, it has some option and it is telling a little bit about what is happening. Here you see the link layer address. Here we are in the router advertisement and there are some options, and we'll scroll down, and with this you see the link layer address or MAC address and MTU, that's 1500, and then the prefix information as well. So ICMP version 6, like ICMP version 4, is very important protocol, but unlike ICMP version 4, it assumes a couple of different roles, and that is because IP version 6 does not use AARP or IGMP, and that is taken care by ICMP version 6. Domain name systems or DNS resides at the application layer of the OSI model. The DNS is an important protocol as it maps a host name to an IP address. It uses UDP port 53 for requests and uses TCP port 53 for zone transfer. With DNS, a client will send a query to a DNS server for an IP address. The server will respond with the information. The server can ask other DNS servers for information. With DNS, there is number of types of records. Some commonly seen records are a type A record. That's for an IP address version 4 address. You might also see a mail exchange record. This will redirect mail to a mail server. A COD A. This shows the IP version 6 address. Now, why is it called COD A? Well, IP version 4 is a 32-bit address. IP version 6 has 128 bits. It's 4 times as large as an IP version 4 address, and that's why it's called a COD A. Within the DNS header, you will see questions, answers, authority resources records, and any additional resource records. Now the question from the client is slightly different from the answers from the server, and we will take a look at that in just a moment. I first want to direct you to this website, and where you can find out a lot more information about DNS. Now within this you will see that there are a ton of RFCs that deals with different issues on DNS, such as here DNS zone transfer protocol or DNS blacklist and whitelist and DNS security and a lot more. So there is a lot more to DNS, but let's just take a look at this simple example. I am at this packet capture and there is a lot of packet. I might just want to filter by DNS, and I will just go to this display filter and type DNS. Now down below you will see that there are 12 displayed. But let's take a look at just one single transaction. I'll go here at the standard query, and when we drop this down, you see the transaction ID. Now it says down below response is 12, and it knows that because it matches that transaction ID. So I will right click and we will say apply as a filter. Now we have them together. Well, now let's take a look at the query first from the client. So using UDP, you see that it offers a high number port and then it goes to the server on port 53 for a query. Now let's drop this down, and here we see the query, and first we see the transaction ID, and then we drop this down, and these are the flags that are set. Now first we see that the first one is a 0. That means that message is a query. Now this flag means recursion desired. Do query recursively. Now there are two types of queries, an iterative or recursive. An iterative query would be a server is unable to provide an answer, so the client has to go back out and retrieve the answer. What I would like you to do is recursive query, and that means the server will look on behalf of the client. As you can see, recursion is desired. Then down below you see I am asking one question, and please give me the IP address of this site. Now let's take a look at the response. Again, using the UDP source port 53 and then return to high number destination port, and then we'll take a look at the DNS. The response, so again we see the transaction ID, so we kept those together, and then you look at your flags and there you see your response. The message is a response and we know that, but then down below the server answers. So as it says here, recursion desired, do query recursively, and the server response, yeah, recursion is available, the server can do that recursive query, and that's good thing. And as you can see, there is one question and 3 answers. Let's take a look at those. Here's the question to find IP address to that website, and then let's go and look at the answers, and I'll pull all these down, and as you can see here the information on all of those answers. You see that there are 3 answers. Within that you can see the time to live value is 220. Now what does that mean? In a DNS header, well, there we have a record that's returned and you have an IP address and you have your answer down below here. That it's saying is that the record that's going to be held in a cache on a server or even at the host is how many seconds it can live in the cache before it goes away. So the time to live value means after 220 seconds it goes away, and you will have to request that information and it will most likely be sent back to you. So there you see a standard query and a standard response. And as we understand, DNS is a very important protocol that provides a host to IP address translation so that data can transact on the network. Dynamic host configuration protocol works at the application layer of the OSI model. The DHCP dynamically assigns IP addresses on a local area network. DHCP uses UDP for transport, and the client will use port 68 and the server will use port 67. The DHCP uses what we call the DORA process: discover, offer, request, and acknowledge. Let's take a look at the DORA process in the Wireshark. I captured this traffic after first going into my command line and I issued an ipconfig release, and then I went back in and issued ipconfig renew. So I got rid of my IP address and then I got a new one. So when we go up here to the display filter, we are looking for the DHCP. Okay, so now let's take a look at the first one. As you can see that the DHCP release, and that means I am giving up my IP address, and you are seeing that what we give up was the .19, and now my client address is 0.0.0.0. Alright, I have gotten rid of it. But then the next step is to go through the DORA process. Now, take a look at the transaction ID. Now we know that I don't have an IP address, so the server keeps track of who I am by that transaction ID and my MAC address. So the first step is to go through the DORA process by saying discover packet will be sent out as a broadcast. Now this packet is essentially saying I need an IP address. Does anybody have an IP address? Now this goes out as a broadcast in hopes that a server will hear and respond. So as you can see that the message type is boot request. I will pull this up and I will tell you that there are a lot of different options with DHCP. But the one I want to show you with the discover packet is the request IP address. What I'm essentially saying in that original discover packet is I like the same IP address what I had before, that .19. Now we see the offer. The DHCP offer comes from a server. Now understand, on an enterprise network you most likely will see two offers responding, so it will come from two different servers. Now the offer is saying I have an IP address and you probably will like it. Why don't you try it? .19. It knows that I want the same one and it says, you know, no one's using it, go ahead, why don't you try that .19. The next step is for the client then go back out and say, you know, I think I do want that one, and let's go to it. So I'm going to request it, and again I want that request IP address here, and I would like that IP address. Could I have it? Well, sure. So the server responds with the final step in the DORA process by sending an acknowledgement, and now I am sending my reply, and again the same transaction ID, and here we say your client IP address is .19. File transfer protocol resides at the application layer of the OSI model. FTP transfers files using TCP ports 20 and 21. Port 21 is the command channel on the FTP server and port 20 is the secondary port used to transfer data. Once you get into the server, you are going to see a series of reply codes, and this will tell us the state of the data transfer. Classic FTP uses what's called an active request, meaning the client initiates that data transfer and the FTP server maintains state information such as current directory and any user authentication. However, most likely you are going to see a passive request, and this is preferred for clients that are behind a firewall as it's more secure, because the client, not the server, initiates the transfer. Basically, the client says to the server, you sit back, I will do the driving. It first asks the server to accept a data connection over a new TCP port, and the server normally accepts the code 229, and then the server will provide a port in which to make the connection. I have this packet capture here, which is FTP, and this is standard FTP exchange of data. Now first of all, I will tell you that it's in plain text and there are very few open FTP servers out there. In most cases, it's using some type of secure connection or encryption, but we will be able to see everything cause it's in plain text. So the first thing you see is the initiation of the content from the client to the server, and there you see the three-way handshake. Now I will go into the packet 4 and I will right click and I will say follow the TCP stream, and we will open this up. And this is very classic. What you see is something on there is a banner which you would read, and it would give some warnings about what the site's about and what you should or should not do. It will provide an anonymous login, and it says send your complete email address as your password. Then once you get in, the anonymous access is granted. However, restriction will apply. Now down below here we see that it is asking for the extended passive. So the client says, could we go into the extended passive mode? Then you see the response from the server 229 saying yes, we will do that. We will enter the extended passive mode, and then it replies with a set of number, and then you will see the complete exchange, and then at the end where it says transfer completed, and that kind of ends it. But let's go into that passive. So I'm going on to the frame 27 and we'll go and open this up. I'm going to go down into the passive mode. So the request command passive, so that's saying from the client to the server we go into the extended passive mode. Then the next packet is 29, where it accepts that passive request, and we will go into the FTP header where it says entering extended passive mode, and you will also see this IP address and passive extended passive port number. Hypertext Transfer Protocol is an application layer protocol for browsing the web. HTTP has been in use on the web since the early 1990s. It's a client-server model that uses TCP port 80 by default, but can use other ports as well. With a typical transaction, the client will send an HTTP request and indicate what the clients want. The server then will respond with the status code and server information and then any requested data. Now, there are several status codes within HTTP, but most of the time we are going to get a 200 or success, meaning everything's okay and the data will follow. Most application layer protocols have a typical format where you have the frame header, the network layer header, and the transport layer header, followed by the data. Now the frame header, the network layer, and the transport layer header remain pretty much the same. The data in the application layer header change according to what's happening in the conversation and whether it's from the client or from the server. So with HTTP, you could possibly get the HTTP header information that includes the general header, request and response header, or the entity header. And then within that you would have the HTTP body, which holds the HTML code or the web page so that it can rebuild that in your browser. On a local area network, the data link layer uses the MAC address of the destination machine rather than the IP address. Address Resolution Protocol resolves an IP address to a MAC address on a local area network. Let's take a look at where ARP resides into OSI model. It resides in between layer 3 and layer 2. And that's because when we take a look at it, it does not have a network layer header. It does not have a transport layer header. It's simply doing a resolution. In addition to the ARP request, ARP replies, you might also see a gray 2 to us ARP, which is a test for duplicate IP addresses on a local area network. If you like to follow along, go to packetlife.net and I select ARP and this last one here ICMP across.1q.cap. I have opened it up in Wireshark and there really aren't a lot of packet in this capture, but we will just take a look at ARP. We will just put this in the display filter. And you see there are a couple of different types. One is the gratuitous ARP, and as we talked about, that is simply a test for duplicate IP addresses on a local area network. But then down below here we see the ARP request and ARP reply. Let's take a look at the request. We'll drop this down and the hardware type is use, and here we can see it's Ethernet, and we see the protocol type IP and the hardware size, which is 6 bytes, and that is the length of the hardware address, and the protocol size is the length of the protocol address. Here we see the OP code and it is a request. Now it's from the sender here, which we can see. This is the sender MAC address and this is the sender IP address. The target MAC address is a broadcast, and remember it does not know the MAC address, so it goes out to everyone on the network. Everyone on the network hears it, but only one should respond. And then down below here is the IP address, and then we see the reply, and it has the same fields except it does provide the answer. Now we see the opcode is a reply and the sender MAC address is a words coming from, and there's the IP address, and then it's responding to one that sent the ARP request. So address resolution protocol sites in between the network layer and the data link layer to resolve an IP address to a MAC address on a local area network. Built within the Wireshark is the expert system. The expert system helps to alert the network administrator on possible issues once a capture has been made. Keep in mind, it's only a guide. Sometimes it really isn't a problem, such as checksum incorrectly calculated. When we go into the expert info console, you will see 4 categories. I say expert info because that's how you might see it referenced. If you go into the Wireshark wiki, now they are in order of severity. The first one is an error. You will see a red circle that indicates serious problem. Yellow indicates warning. That means there's possible problems. You will probably want to look into them. Cyan are notes of interest and the blue are chats, which is typical workflow and state changes. Now I have opened up this packet capture because it's a pretty good example as it lists all 4 categories. Now if we take a look in the lower left corner, the red circle indicates the highest level of threat, that there is possible serious problem. So let's go and select that, and you can see this red, it is severity is error, because if this is red then that means that severity is error, so you have to fix this. And if I just extend this, you will see we have couple of other options like encrypted alerts, encrypted heartbeat, and we can change stuff and we can fix these stuff. Other than that, yellow you will see warnings, so the severity level in yellow is warnings. So again you can just expand this and you can just fix this stuff and you can see all the warnings and stuff. Next one is the cyan, which is notes. You can see we have all the notes here, and the last one is blue, which is chats. And you can also change the severity level from low to high or high to low. Okay, so the expert system provides insight on possible issues in the packet capture. Wireshark groups are reporting by level of severity, and that includes error, warning, notes, and chats. Wireshark has many built-in tools to help the network administrator identify and troubleshoot network latency issues. Tools that includes the expert system, coloring rules, the intelligent scroll bar, and the time values that are built into Wireshark to identify gaps in transmission. Within the expert information, there are several things that are cause for concern. That includes zero window. That means that the client is unable to receive any more data because the buffer is full. Now on the client side, that might not be a big problem, but if it is a server, this could cause major bottlenecks. Keep alive that are saying keep this session alive and duplicate acknowledgement where the client is requesting the data over and over again until it receives it. Retransmission or fast retransmission, or what we call spurious transmissions. A spurious transmission is a data that is sent again even though it's already been acknowledged, and that is because the server somehow did not get that acknowledgement and it sends the data again. High latency can be caused by any number of things such as processing delays, distance itself, and something called buffer bloat. This is a queuing delay in that the router buffers get full and the packets are simply dropped and there's a gaps in delivery of the data. Welcome guys. Right now I want to save these packets. Now there are a couple of ways we can save this packet. The first one is very simple. If you want to save the complete file, you can just simply go to files and click on save as. So you can just click this and you can name your file, okay, or you can override any other file and then simply click on save. Now what if I want to save the specific frames? Okay, let's say I want to save the frames which contain ICMP protocols. So we can use display filter or we can also use mark. So you can see this mark packets. Okay, so first of all, let's say we want to mark something. Let's say we want to mark this one and this one. So you will see that this one is here and this one is down below. Okay, we have these two in between these two. Okay, so we can just simply go and click on mark. So it will mark this packet. And again, if I want to mark this one as well, we can just click on mark packet. And if any packet has been marked, you can again just click on and it will unmark this. So again, let's mark this as one, and you can mark all of the packet which you want to save. Okay, and another thing you can do is you can use display filter. So let's say I will just select all which have protocol ICMP. So let's just display filter this. So right now we got all the frames which have ICMP protocols, and you'll see it also have this marked one. Okay, and now if I want to save all of this, we can just simply go to file, and here you will see export specified packets. So if I just select this, now I can name my file and I can also overwrite any one of this. Let's say this new file, and after that, here you can see it contains all the packets here, and you can just select the marked packets only. So if I just select this, it will only save the marked packets, not all of these. Okay, and if I just select all packets, it is going to select all the packets. You can see we have 2 packet marked and first to last marked 2, and we also got selected packets only 1. Okay, so if I only want to save the selected packet, I will just click on this. I want to save also, let's click on all packets and let's save this. Okay, and now we'll just remove this display filter and we'll close this, and again let's open the file we just created, we just saved. You'll see this new file pcap, and we'll open this, and now you can see we only have all the frames which contain ICMP protocols.